Now, these are different factors that influence the rate of diffusion, okay, and this is understood or explained typically by using a law that is called the Fick's law. And there is a formula, and let me tell you, you don't need to memorize the formula. You won't have to calculate anything. The only thing that you need to use that formula for is to understand which of those factors are directly proportional to the rate of diffusion and which factor is inversely proportional to the rate of diffusion. Notice that the rate of diffusion depends on the surface area, okay, depends on the concentration gradient, difference in concentration, and depends on the permeability of the membrane. If we increase either the surface area, the concentration gradient, or the permeability, the rate of diffusion is going to increase because they are directly proportional. Now, the rate of diffusion is inversely proportional to the membrane thickness. Okay, so a very thin membrane will allow a faster diffusion, while a thick membrane will only allow diffusion very slowly. And that is something that makes total sense. Okay, when you study, for example, the different tissues, okay, when you see a histological image of the lung and you see the alveoli in the lung, you're going to see that there are very thin cells separating the air in the alveoli from the blood, because we need oxygen to pass very fast and CO2 to leave as fast as possible. Okay, imagine that someone makes a mistake and instead of putting this squamous, simple epithelium in the alveoli, they put there a columnar epithelium or a stratified epithelium. How can oxygen enter rapidly through 10 layers of cells? That would be impossible. Okay, so the thickness of the membrane is the only factor that if we increase it, will decrease the rate of diffusion. Of course, large surface area, okay, if you put together all the alveoli, you have a huge surface area for diffusion of respiratory gases. If you put together all the intestine, if you, for example, start extending, okay, all the small intestine epithelium, okay, you're going to have a huge surface for absorption. Okay, if we start, someone does surgery and remove part of the intestine, now we have less area. We are going to have less absorption. If someone has to have a lobe of the lung removed, now they have a smaller area for the diffusion of the gases. And that will have consequences. Okay? Solubility is depending on the molecules, lipid soluble, non-polar diffuse more easily, oxygen, CO2. Smaller substances, faster. If they have high solubility and small size, of course, they are going to diffuse even faster if we have a combination of those characteristics. And this diagram here is comparing simple diffusion and facilitated diffusion, so you can understand the implications, okay, of what we mentioned before. On the left side, okay, we have a diagram, okay, that represents simple diffusion. Remember, in simple diffusion, while there is a concentration gradient, the diffusion will occur. Okay, if there is a greater concentration, the diffusion will occur faster. A greater gradient or difference, the diffusion will occur faster. Okay, theoretically, it can be infinite. Okay, occurs in a linear fashion. In the case of facilitated diffusion, notice that it occurs faster. Okay, here we have a slower increase. This occurs faster, but there is a moment when it doesn't matter how much you increase the concentration gradient. Okay, we are not going to increase at all the rate of diffusion. This is the moment when all the transporters are saturated. And that is something very similar to things that maybe you studied in the past about enzyme kinetics. Okay, when the enzymes are doing their job, Doesn't matter that you put more reactants there, there is not going to be more product. Enzymes are busy. They are doing what they have to do. You have to wait until there is free enzyme so it can get more reactants to continue working. Okay, below you have more explanations about what this means. Okay, and all these concepts here, Km, Jmax or half Jmax, are things that we use typically to know about the affinity of the transporters for the substrate of the transporter. Okay, and these are concepts that are applied in pharmacology, okay, when you are investigating about medications, etc. Okay, but it's not necessary that you enter into studying that. Simply remember what is the meaning of this stop here. Okay, here the Jmax is when all the transporters are saturated. So it doesn't matter if you increase the concentration, okay, of the substances, the concentration gradient, there is not going to be any more transport, or the rate of transport is not going to increase.